Hello everyone, welcome to TriTea. Today we're going to solve two interesting problems, step by step. So let's begin with the first one.
All right, let's jump right into this explainer. We're going to explore what is arguably the most critical bridge in programming, the one that lets your code step out of volatile memory and actually save data permanently. Because let's face it, the harsh reality of software is that the exact moment a program finishes, or worse, your computer suddenly loses power, all the data held in standard memory just vanishes. Poof, it's completely gone. So today, we're mapping out the architecture of file handling. This is the vital process that literally lets your applications log history, save states, and actually communicate across time.
Think about this for a second. How exactly does a massive bank database survive a sudden power failure? It's a pretty high-stakes scenario, right? Imagine if every time a server crashed, millions of financial transactions were just wiped from existence. No way. Computer systems are incredibly fragile when they rely solely on active electricity. A power outage kills everything in active memory instantly. And the answer to this problem? Well, it isn't just building better batteries. It's a completely different approach to how and where we store data while a program is actually running.
So to really anchor our understanding here, we first have to define where that data actually goes to live long-term. We're talking about persistent, permanent memory. Unlike the temporary electrical charges used by your computer's processor, persistent memory relies on physical magnetic states on a hard drive or trapped flash states on a solid-state drive, an SSD. We're talking about an actual physical or structural change on the disk itself. Once your data is written here, it safely survives shutdowns, reboots, you name it. Now, let's quickly contrast these two environments because understanding this dynamic is exactly why file handling is the ultimate non-negotiable solution for your code. On one side, we have volatile RAM. It is incredibly fast but strictly temporary. It gets completely erased the second you hit shutdown. Then, on the other side, we have persistent storage, your SSDs and hard drives. Sure, they might be a bit slower to access than RAM, but they are permanent. File handling is basically the deliberate act of building a bridge between these two worlds. It's how we move data from that fast but fragile RAM into the slow but safe persistent storage.
But to really grasp how this works under the hood, we need to completely shift your mental model. Seriously, throw away the idea of files as boring, static documents just sitting in a folder on your desktop. In programming, you absolutely must start thinking of files as dynamic, flowing streams of bytes. A file isn't just a dead block of text. It's a living destination or a source for a continuous flow of data.
Actually, let's use the oil pipeline analogy, because this perfectly visualizes how we physically connect our program to the file. Imagine your program is an oil refinery processing data, and the file on your hard drive is an oil reservoir. You can't just magically teleport the oil from the reservoir into the refinery, right? You have to physically connect them using a pipe. Well, in programming, that pipe is called a file stream. If you want to write to a file, you use an output stream. Data flows out of your program's variables, through the pipe, and squirts right into the file on the disk. Want to read? You use an input stream, and the data flows from the disk back into your program.
Because we're dealing with this physical pipeline connection to the operating system, there is a mandatory three-step ritual. And I mean mandatory. Absolutely every programming language must strictly follow this. Step 1, open the file. This connects the pipe and requests a specific mode, like read, write, or append. Step 2, read or write. This is the pumping phase, where you actually push the data, the characters, the lines, the raw binary bytes, through the pipe. And finally, step 3, close the file. You absolutely must disconnect the pipe.
Here's the absolute crucial point though. Forgetting step 3 causes complete disaster. If you break this ritual and forget to close the pipe, the data you thought you saved can get trapped in temporary memory buffers and never actually make it to the physical disk. Even worse, the operating system might just lock the file indefinitely, preventing any other applications from accessing it until your entire system is fully rebooted. It's literally a critical memory leak just waiting to happen.
Let's ground this theory in enterprise reality for a second. In production software engineering, you almost never hard-code data into a script. You're not going to sit there and type 1,000 customer names directly into your source code. Production software relies entirely on files to decouple data processing from the physical limits of your computer's RAM.
To put that into perspective, imagine needing to analyze a massive 100 gigabyte database of user transactions. You simply cannot load that entire data set into an array. It would completely exhaust your computer's RAM and crash the entire system immediately. But through the magic of file handling, your program can open a stream, read just line 1, process it, overwrite that tiny bit of variable memory, read line 2, and just keep going. By streaming the data, you can process a massive 100 gigabyte file using only a few kilobytes of RAM. It is the ultimate efficiency hack.
So to summarize our core architecture before we dive into how to apply it, files act as the universal language of the entire software ecosystem. They allow us to process massive data seamlessly. They let our systems survive power failures. But maybe most importantly, they automate interoperability. Because files are universal standard, a Python web crawler can scrape data and save it to a text file. Then, a Java program can open that exact same file to run heavy data analytics. And finally, a low-level C program can read that same file to control high-speed machine hardware. Files completely break down language barriers.
Which brings us to our core design philosophy for this explainer. Logic is universal, syntax is just the dialect. That pipeline analogy and the mandatory three-step ritual, those never change. But the way we type it out, oh boy, that's about to be one of the most drastic syntax shifts you can witness. We're going to conceptualize writing the exact same text, the word TriTea, into a file named data.txt, using 3 very different programming mindsets.
First up is C, which we'll call the architect. Here, you build the pipe manually using functions like fopen and fprintf. But notice the raw construction environment here. There are absolutely 0 safety nets. Working directly with the operating system at the raw memory level means dealing with low-level file pointers. You have to manually check if the pointer is null. If something goes wrong while writing and you don't explicitly handle it, your program simply fails silently, or it just crashes, leaving that pipe wide open.
Now contrast that raw danger zone with Java, the builder. Java treats file handling with absolute architectural paranoia. It requires you to wrap your stream in multiple nested classes. Picture a raw file writer wrapped completely inside a buffered buffer writer. More importantly, it rigidly enforces safety. If you don't wrap these file operations in a strict try-catch exception cage to handle input and output errors, your Java code will flat out refuse to even compile. You still explicitly open, write, and close, but man, it is heavily guarded. And then finally, we have Python, the poet. Python strips away the low-level pointers of C, and it completely throws out the massive nested wrapper structures of Java. Instead, it introduces a brilliant mechanism called a context manager. But here's the real magic regarding step 3. You don't even have to type a close command. The context manager guarantees that the exact millisecond your code drops out of its operational block, Python automatically closes the pipe for you behind the scenes, even if the program encounters a massive error.
Let's synthesize all these syntax differences cleanly into this matrix. As you can see, the core logic is identical, but the approach is vastly different. For tracking, C uses raw file pointers, Java uses nested writer objects, and Python uses a simple file handle. For safety, C requires manual checking, Java forces strict try-catch blocks, and Python automates it through context. And for cleanup, C and Java demand manual close commands, while Python handles it automatically. It's just a perfect visual of how complexity scales from raw memory tracking in C to highly structured objects in Java to clean abstraction in Python.
Ultimately, file handling is what makes software truly powerful, permanent, and interoperable. You now know the pipeline, you know the 3-step ritual, and you've seen how the mindset shifts across 3 major dialects. So I'll leave you with this final thought. If files are the universal language of the digital world, what software ecosystem will your code communicate with next? The pipeline is ready. It's time to start pumping the data.
Across all modern programming languages, the underlying logic of creating and writing to a file remains identical, only the syntax changes. Look at this diagram showing a standard file creation script. We want to delete the predetermined hard-coded file names, like notes.txt, from our code. Instead, we hand control directly to the user with a flashing prompt on the terminal, letting them name their own files. Once the user types that name, the operating system stands by. It takes that exact terminal input and generates the corresponding empty file physically on the disk. This connection establishes a data stream. Whatever the user types next is sent down this pathway, pumping continuously into the new file until the system receives a specific command to stop. Mastering this continuous stream shifts the program from a fixed sequence of code into a tool that adapts to whatever input the user provides. To manage the complexity of opening these streams and handling potentially infinite user input, we need a clean, step-by-step algorithm. This split screen breaks down our 5-step pipeline. Step 1, we prompt the user via the terminal to type a custom string. The program captures this input to use as the file name. Next, we open the data pipeline in write mode, designated by a W. This specific mode commands the system to either generate a brand new file with the user's chosen name or overwrite an existing one. Step 3 establishes a continuous listening loop. The program waits at the terminal, actively capturing each new line of text the user types. In Step 4, that captured text must be written immediately to the file. We append a new line character to every single entry as they travel down the stream, ensuring the lines stack neatly rather than smashing together into an unreadable block. But if the user can type as many lines as they want, how do you safely terminate an infinite listening loop when you don't know the final number of inputs? Step 5 triggers the termination condition when the user inputs an empty line. The loop breaks, formally closing the stream to ensure all data is flushed and safely saved to the disk. Visualizing this 5-step pipeline provides a reliable mental model for handling data streams. The exact commands will change depending on the language, but this sequence never does. Let's prove this logic by running our algorithm through universal pseudocode. On the right, we have a tracking table to monitor how our variables and streams behave during execution. During the initialization phase, the program requests the file name. We capture mygoals.txt, update the variable, and the stream opens. We enter the continuous loop. The user types their first line of text, learn C. It meets our conditions, and the text is written straight to the file. On the second iteration, the pipeline remains open. The user types master Java, and this new string data passes smoothly down the stream. When the user presses the enter key without typing a message, the code detects a string with no content. This triggers the break command, ending the loop. We execute the cleanup phase, formally closing the stream and securing the data permanently on the hard drive. By internalizing this specific dry run logic, you possess the exact pipeline needed to implement dynamic file streams in any modern coding language you choose.
Now let's see how the code looks in C. in Java. In Python. Let's now move to the second one.
Here is a standard text file, a computer terminal window, and a user. Today, we are building a mini file browsing utility to connect them. The first half of our program's job is straightforward. It prompts the user for a specific file name and searches storage to verify if the text file exists. Once located, an interactive menu presents two choices: read raw text inside the terminal or launch using an external editor. At its core, this utility acts as a traffic cop. It accepts input, evaluates the options, and safely routes data based on the user's choices. This basic routing mechanism is a universal task in software development. Before writing any code, we need to map out the program's logic using simple English steps. Here in this flowchart, you can see our first two steps highlighted. Step 1 requests the file name from the user. Step 2 attempts to open that file in read mode. If the file is missing or fails to open, the program displays an error message and safely halts right here. If the file does exist, we move to Step 3. The program presents the interactive menu, branching into Option 1, Read in Terminal, or Option 2, Launch in System App. Step 4 defines the Option 1 pathway. The program initiates a loop to read the file sequentially, grabbing characters or lines from the stream one by one and printing them directly to the terminal screen. Step 5 defines Option 2. Instead of reading the text internally, the program closes the file stream and sends a command to the operating system, requesting it to open the file in its default native editor. Consider the sequence here. Why must the program strictly check if the file exists in Step 2 before ever attempting the reading loop in Step 4? Attempting to pull text from a file stream that does not exist will cause a fatal program crash. By establishing this exact sequential logic, verifying the file before accessing it, we prevent structural failures, regardless of the programming language we use. As the text on screen says, logic is exactly the same everywhere, only the syntax changes from language to language. This split-screen diagram lays out the universal pseudocode for the Option 1 pathway. On top, we see the command to open the file stream, followed by a while loop block that handles the reading process. Let's run a test. A user selects Option 1 to open a file named recipe.txt, which contains exactly one line of text. The program successfully locates the file on disk and opens the input stream. Before attempting to read any data, the while loop checks a specific condition. It verifies that the stream has not yet reached the end of file, or EOF marker. Think of this marker as a physical stop sign sitting at the very end of the document's text. Since the stream is just starting, the condition is met. The program enters the loop, reads the single line of text from the file stream, and prints Step 1, boil water, directly to the terminal. The loop then restarts, but this time the stream pointer hits that EOF marker, the loop condition evaluates to false, and the code execution immediately breaks out of the loop block. There is one final action required. The program executes a stream cleanup, safely closing the file pointer and disconnecting the data pipeline. Look at this summary. We have a three-phase flow: input and open, menu choice, and read loop followed by close. Mastering this exact sequence equips you to handle files safely in any modern programming language.
Now let's see how the code looks in C. in Java. In Python. Comparing all three languages, C, Java, and Python, we can clearly see how the core logic is same in each three. Just syntax is the one which changes.
Here,
Thank you for watching. See you in the next video.
Subscribe now.